everyone, this is Julia. So this is going to be a video walkthrough of the slides from Lab 9, which are about trees. So trees, like linked lists, which we learned about last week, are another recursive data structure. And I think trees are really interesting to learn about because there are so many different things that you can use them for with data. And there are a lot of reasons why they're a really good data structure to use in some cases. So we're going to be learning a little bit about them this week. And yeah, let's get right to it. So some announcements before we start. Congratulations on finishing Maps, our first project of the semester. We're going to be releasing the second project very soon, and it's related to the game called Plants vs. Zombies, if you've ever played it. If you haven't, it's a really cool game, so if you're looking for a game to try, it's a really cool one. But besides that, we're going to learn about trees. Alright, so like with any new topic, we typically start with definitions and terminology to get a sense of what we're dealing with. So I'll start with the picture of a tree. So trees usually work like this. You typically have nodes, which are these circles in this picture, and the nodes represent basically any element. It can be the very top element, the sub-elements, or anything like that. And then the numbers inside them are the actual values that are associated with those elements. So here is the value of this node. And the nodes themselves can also have special names. So the one at the very top, this node, is called the root. And you can kind of see it because it's the node which all the other nodes come from. So although trees are called trees, it's kind of a little bit upside down when we look at a diagram of them. So the root is actually at the top, whereas they would normally be at the bottom. So the root is at the very top. And then the leaves are going to be at the very bottom. So leaves are just nodes with no nodes coming out of it. So you can see basically they're like the end, the very bottom. So these nodes that I'm highlighting are the leaves of the tree. And you can tell because there are no other nodes coming down from the nodes. So it's not like this one has one over here. So yeah, that's what it means to be a leaf. And what else? Okay, so and then we have branches. So branch just means any sort of descendant. And when I say a descendant, I mean it's the node that comes down from another node. So for this 3 node, it has 2 branches because it has one node coming down from its left side and then one node coming down from its right side. So it has 2 branches. And you can see both these branches respectively have their own 2 branches. So one over here on the left side has 0 and 1, and 2 over here has 1 and 1. And then this one right here also has 2 branches, but the rest of them are just leaves. Okay, so I think we covered all the terminology, just making sure we didn't miss anything. Yes, so branches are subtrees. So I'm going to just reiterate, and we're going to touch upon this in the code. Each node itself is a tree, but together these subtrees make up this entire tree. Okay. And so nodes are the circles, and the value is within them. And leaf nodes have no branches, so there are no descendant nodes from it. Okay. So you can probably start to tell how recursion is going to play out using trees, because this is a tree element, this is a tree element, so they're all going to be tree objects, and recursion is going to play out very nicely with that. Okay, so here's the actual class, or how typically we define it. So we have a class tree, and its init method takes in 2 things, which is entry, and this is just the name for the value. So it would be like 3, 1, 2, 0, 1, something like that. And then the branches. So branches, we expected if there are any branches, it's going to be in a list of some tree object, yada yada, maybe another tree object, yada yada. It can be however one wishes, but it's going to have tree objects in it. And if it doesn't have any branches, it's going to be the default empty tuple. And then we have self.entry equal to entry, so it's just going to set the attribute. And then it has a for loop going through the branches, and then asserting that each branch is an instance of tree. So we're just making sure that we haven't maybe put in some wrong input, like put in a linked list when it was expecting a tree or something like that. And then self.branches is going to be the list of the branches. Yeah, so that's pretty much it. All right. And then for the class, we have a function called isLeaf. And basically what it does, it checks whether or not self.branches is empty. And if it is empty, then it returns true. Because with a leaf, we're expecting that it has no branches at all. So it turns true if no branches. All right. And then here are some examples of using the tree constructor. So this makes just one node, has the value 1 in it. And then this line over here will make a little bigger tree. So, oops, that's not going to fit hello. So I'm going to write hello for our root node. And then the branches are going to be 2 nodes, one saying CS and then one saying 88. Okay, so that's how the constructor works. And for a little bit longer example, here's what the example we looked at, how it would be called with a constructor. So first we are going to make the root node, and that's the very outer call to tree. And then it's going to have its branches. So this entire list over here is going to be the branches for 3. So it's kind of hard to read sometimes, but I like to just break it down into different pieces. So I try to figure out where is the left side and then where is the right side. So I can see here that we have a comma dividing these 2 sides. So we have one left side and then one right side. And then the left side, we can start with that. It has a 1, and so that makes up this part of the tree. And then this one node also has 0 coming from it on the left side because it's the first element of the branches list. And then it has another tree of 1, and that's the right side. All right. And then similarly, if we go to the right side of the root, so I'm talking about this node over here, it has branches of, on the left side, it just has one branch or one node of value 1. And then it has a pretty long tree on the right side. So it's a node of 1, but that node of 1 also has branches of 0 and 1. So 0 is on the left side, 1 is on the right side. And that is how we read the constructor calls to make this diagram. So it can be kind of tricky, similarly to linked lists, reading them and figuring out which element is which. But you can always try to break it down into left side, right side, and figure out which one are the branches and which is the element or the value. Okay, so we're going to do a quick example, or a pretty straightforward example, I hope, of a function that's going to mutate a tree. So we have this NewGate function. It takes in a tree, so this is going to be our tree. And typically this is the root of the tree. And with the root of the tree, we know its branches. And with the recursive data structure, we can then look at the branches and we know their branches. So really, by just knowing the root, we can get the entire tree. So usually this is the starting with the root. Okay, and then it's going to set t.entry to the negative of that. So what it's doing is just negating the entry of the tree. And then it's going to recurse using the function on each of the branches of that tree. So we can start to think about this function. For one thing, it's kind of maybe suspicious looking because it has no base case. Usually with recursion, we're looking for like some if statement to stop the recursion whenever it needs to be stopped or whenever the recursion has finished. But here we don't have any if statement, so maybe it looks incorrect that way. But one thing about this function is that when we're talking about trees, we know that when we get to the leaf or the very bottom of a tree, it's going to have no branches at all. So the branches list is going to be totally empty. And so this for loop is not going to even run at all. So let's say I have like 1 and 2 and 3. And let's say I've already completed this node, calling negate on it. Now I'm at this node. So when I'm looking at the very bottom leaf, which is 2, I'm going to just negate it over here. And then when I call for b and t.branches, t.branches is going to be empty. So this for loop never runs and it's just going to finish the function. And that's why we don't need a base case at all, because when it reaches a leaf, which is the very bottom or the very end of the recursion, it's just going to do nothing, which is the same thing as stopping the function. Okay, and then why is there no return? Well, that's because we want to negate the original tree and not make a copy of it. If we wanted to make a copy of it, we can actually call the constructor and pass in the negation of the entries of the original tree. But here we actually just want to change the original tree and not make any copies or anything like that. So we're not going to return anything. And one thing people ask me in office hours is like, why is there no return? I'm changing the original tree, but my test case are failing because I'm returning something. One thing, it's totally okay to return something, but it's just not necessary. So our tests usually make sure that you're not returning anything, because chances are that if you are returning something, you probably maybe were making a copy or something like that, and making a new tree that gets returned. But if you're changing the original tree, you don't need to return anything because the changes are going to be with that original variable, and we can just call it and we know it's already modified. So that's why there's no return here. Okay, and the last question is, what does this function do? Well, it just mutates the original tree by negating all the elements. And that's pretty much it for trees. I hope this was a helpful introduction to trees. One last thing I want to say is that with these recursive data structures, it can be quite challenging to work on the homework problems or the lab problems. And I hope you don't feel discouraged